Hey guys, welcome to the beginner C and C++ intro series. In this series, I will try to demystify C and C++ in a way that is more computer science oriented and gives you a clear picture that separates between the high level languages and lower level languages and their use cases. That being said, like high level languages, they have their own specific use cases. You want to write less code, you want to achieve more things. So it would be probably better that you group some tasks that are repetitive in general and just use a single line of command to do that task. On the other hand, lower level languages are more focused towards getting that fine grained control over your hardware, triggering the particular circuits and getting what you actually want to do. So before we jump into C and C++ and all this stuff, uh, we should focus on we should gloss over some tiny concepts of what a computer is and how it actually works. So, like a very basic computer architecture consists of three major components. One is your input and output. That is basically whenever you are typing something in the keyboard and you're using your mouse and stuff like that. Those things they are considered as input devices, and your monitor and sound system they're considered as output devices. Now these devices have like these are hardwares. Okay, basically these are hardwares, and these hardwares are connected to your system via a software called driver. And driver is a kind of software that interprets these hardwares to your operating system and enables you to use them in your application, like you want to listen to your keyboard's input or your mouse's input, or you want to output something to your screen. For example, like for graphics, for example, let's say for graphics, we have like let's say for Windows we have DirectX or OpenGL, or like we have Vulkan for low specific VUL. I think I don't remember the name, but the idea is this: these are the drivers where your hardwares, although like in this case, like graphics card and hardwares, they're not typically your like input output devices. They are kind of processor, but we'll come into it. But just to give you an like overview of the difference between a hardware and a driver. So like the graphics hardwares will be your basically graphics card. For example, you have your NVIDIA GPU or AMD GPU and so on. So these are the hardwares, and the drivers. They give you access to some API. API stands for API stands for Application Program Interface. Okay, and what Application Program Interface does is it gives you a way to write some code that, when executed by the computer, will trigger a specific action, the like a circuit action in the hardware, and will produce some kind of result. But so that's like the basic things. The next thing is that in a computer, the most important thing is your processor. Basically, you can't create a computer without your processor. Now, a processor, what is a processor? Processor is kind of like your computer's brain. For example, let's say your Intel Core i5 or i7, whatever you have. Okay, this is an example. And what it consists of two things. The first thing is you have like an ALU, which stands for arithmetic logic unit. So what is an arithmetic logic unit? It can not only perform arithmetic, but it does like arithmetic uh, calculations as well as logical calculations. For example, like comparison is a kind of logical operation, and arithmetic operations, like a very simple example will be addition. Okay, so these processors, they have like these things built in, like they can do it in how do I say, like these are done directly hardware. Okay, and how they do it is that they use let me go down. So what they do typically is you have these things called gates. Okay, and a typical I'm taking three gates example here. One is OR gate, and one is AND gate, and one is NOT gate. So as you already know that computer reads and writes stuffs in zero and ones. Like it knows everything in zero and ones. A zero is basically means that circuit or a switch being on, and a one means that a circuit or switch is off. So depending on the behavior of two switches, you are trying to determine the behavior of the third switch. That is what a gate is basically doing. So you have OR gates where if the both switches are on, or like any of the switches are on, in that case the output switch will be on. In case of AND gate, what you will get is like, for example, if like only the both switches are on, like A and B, that A has to be there and B also has to be there. That way only A and B will be true. So AND gates do that kind of thing, and NOT gates are very simple. Like what not to do is basically they say that if you have zero, then take it to one, and if it's one, then make it zero. So these are the basic gates. Then there are some other gates, like for example, you have NAND gate, which is nothing but an AND gate with a NOT gate, and a NOR gate, which is a NOR gate, an OR gate with a NOT, with a NAND gate, and XOR and XNOR. We will come to these things later. But that's what gates are, and gates are basically created by your transistors. Okay, transistors are those silicon chips, and your processor is basically a metropolitan city of these transistors, which are not actually made out of like thousands of OR or thousands of AND and thousands of NOT gate, but most probably they are made of like OR of them, all of them are NAND gates basically. So you can combine these gates together. We can get into a separate video if you want about that. But these operations I will show you. But the basic idea is that, and these gates they allow you to manipulate the particular signal to depend on other signals to make it on or off, and that is the basic idea behind the whole computer architecture. Now when you arrange these gates all together, you come up with something like an ALU, which will be able to do operations like addition, subtraction, multiplication, division, modulus. It will not be able to do exponential, by the way. Okay, so that you have to design, like you can define addition, exponential in terms of multiplication, like n times multiplication, that is basically. And then there are logical operations that it can perform, and what a ALU typically does. And before we come into that, the processor has another two parts actually. So one is control unit. Control unit is basically thing that interprets whatever like instruction you have, whatever instruction you are trying to provide your computer, and interpret it, and by that interpretation it triggers the particular circuit that is required to do that operation. And that comes to the third point, is that whenever you are doing some operations, you need to store the values somewhere. And that's where the fastest memory of the computer that resides within the processors come in. And they're called registers. So registers are nothing but memories. You can think of them like a bunch of switches, like you have few switches like this. And some switches have the value 0, some switches have value of 1, and so on. And when you're saying about a 32-bit system, what a 32-bit system means is that in case of a 32-bit system, for a 32-bit system, your registers are typically storing 32 zeros and ones. It might be 0 and it might be 1, but you have 32 slots of these things. So system, there are 32 slots per variable, and these slots in computer science term we call them bits. Okay, so one bit can be 0 and 1, and then in 64-bit system, that is equivalent to 64-bit, 64 slots. The idea of like a program being executed in a computer is that you have heard of something called as a ROM. Okay, and ROM stands for read only memory. It's a chip that contains the translation of all the instructions and their correspondent operations. For example, your computer, it has some registers like, for example, like, I'm just making it simple down. You don't have like A and B, something like RX and something like that, RX A, RX B. That's like, but you have some registers like A, B, and so on. And you have a special register called accumulator. Okay. So what accumulator does, let's say this is a simplified computer that has an accumulator, an A and B, and an ALU. So what happens is your ROM has something like this. This is just a demo, like 0010, and this corresponds to the instruction of addition. Okay, addition, ADDITION, addition. And what happens is that when you want to perform an addition, you have to specify another two values to do the addition. Okay. So what happens is that in your system, what computer understands is something like this. You have these things called are micro instructions, and micro instructions are nothing but a sequence of zeros and ones that determine what the CPU is going to perform. For a typical small example of micro instruction, let's say addition. We have a 4-bit system. That means we're not talking about a 32-bit system, where 001 means add. And then you have like two locations where your variables should be. Like let's say this location is X and this location is Y. And this X and Y, they are in your main memory of the computer. Like after processor, the third part that comes that is very important is your main memory. And the main memory is nothing but your RAM. Some people call it volatile memory because it gets swapped whenever you are creating a variable, a constant, anything in your system that is running, that is not stored as files in your disks. They are in your main memory. And we'll talk about main memory later, about how they work and typically do. But now to start with programming, you need to understand how a processor works at first. So, as I was saying, the ROM has this instruction 0010, and it means addition. And who interprets that it means addition? That task is done by the control unit. Control unit sees this line that something like this has come. Let's say 0001 and then 0100 and then 00, let's say 10, for example. So what it does is it says the first part and it knows that okay, I have to do addition and the next two sequences. And by the way, these are not spaced between like this. This is a continuous sequence of zeros and ones. But I'm spacing it to say that this is a 4-bit system, nothing else. So in this 4-bit system, it first sees the control unit first sees that you have 0001 as your first micro instruction. And what it does, it knows that okay, when 0001 is there, the next two 4 bits will correspond to the x and y location of the memory. And if you know the binary system, we will come to that. But basically, like you can think of it like this: 0 is 0, then 1 is 1, then you have to define 2. So 2 will become 1 0, 3 will become 1 1, and so on. Okay, so like that. So they interpret this, and they know that at these particular locations or addresses in your RAM, there are two values that are stored. Let's say that they are x and y. So first, what they do when this control unit sees this instruction, it says that okay, first what you need to do is you need to, and these locations in this case will be present in your memory, not memory, but your registers. Okay. So what it says that okay, this x value is some, let's say, I'm giving an example, so I'm just boiling it down. So let's say this is an x value and this is an y value, and I just want to add them. So what it will do is first it will load x into that a register, and it will then load y into that b register. It doesn't need to load actually, it will just load y in the accumulator register. And whatever then what it will do is it will take the value from the a register, take the value from the accumulator, and send it to the ALU. And ALU will perform the addition, this addition performance, and whatever the output of ALU will be produced, once again, it will be stored to the accumulator. And that's how a typical instruction is executed. As a programmer, it's very hard for us to like keep on writing one after another in things like in zeros and ones. So what we do is we write a kind of program that's called a compiler. Compiler takes a human defined language like let's say I want apple and something like that, or add two numbers or something like 2 plus 3, for a simple example, and it converts this 2 plus 3 into that instruction, like our additions code was 0001 in this case. And let's write this 0001 for example, and then it has to give 2. So it is 10010, because like obviously it's 4 byte read at simultaneous time because it's a 4-bit system, and then it has this 3-bit system. So a compiler is actually responsible for converting this thing into this thing. Now, this kind of compile this particular conversion that is happening here, and this is what we call, because it's very near to the computer, we call it machine code. And sometimes we just write it as like a directly assembly code, like human readable, and in that case it will be like this add 2 3, for example. I'm just giving you a simple example. It will be more like some registers. You will say load to load, like load the hexadecimal value of address into load the hexadecimal value of 3, and then do addition. But the idea is that the micro instructions, they are very hard to write by the humans. So they use a system called compilers, who first parse this code, boil it down to assembly code, which is also human interpretable. But as the assembly code grows, it's very hard to like understand and optimize them. So compiler then performs some optimization on these things, and it produces something called as an object files. And these are nothing but the translation units in translation units, for example, in compiler's terms. So what a translation unit is, it contains some code that can be directly converted into assembly. Now, every in general case, every file that you send to the compiler uh, produces one translation unit, and then you have multiple sets of translation units, and then there is another software called a linker. What linker does is it links all the translation units, and then gives you a binary code that is an executable file. What a binary code looks like, if you want to like have a general overview, it's something like that you have different sections. Like you have first global section that defines the start of your program. So let's say it will say like global start. This is I'm writing in assembly, like what the actual code looks like. Now for global, there will be a particular binary value. For start, there will be a particular binary values. And once again, these values will be interpreted by your control unit. Okay. And then depending on the interpretation, it will load different values from your random access memory or RAM to your CPU, to your registers of your processor that are the fastest memory available. And in between them, just to inform you, another term is cache. And what cache is faster than RAM but lower than the registers, like in terms of speed. So, and caching means that to be able to reuse memory. So sometimes what happens is that the value is already present in the cache. In that case, it will not go to the main memory and load it again, but it will just read the cache value and update those values in the registers. We'll talk about cache in some later videos, but for now, you have to understand that these are actual hardwares that are sitting inside your processors and that are doing all the stuffs as goes for main memory. And what you are going to write something like 2 plus 3, for example, which is an expression or code in terms, in simple terms. And that code is being taken by the compiler, and for every file, most likely for every file you are getting something called as a translation unit. Okay. And then these translation units taken by another program. It's called a linker, and program means application, nothing else, called linker. And they take all those translation units and all other libraries that are inside your system. It might take separate lib files, for example, just putting it here, or something like .dlls, dynamically linked libraries, etc. And then it patches up everything together and creates an executable file, that is your exe file. And that's how typical difficult software is written, and then it's converted to machine code that is understandable by the system. And then what happens is this machine code that is here, this machine code is interpreted by your control unit of your uh, processor, and to interpret that it will consult your computer's ROM that has all the instructions, like instructions, and for all the instructions what you have to do stored inside them, like how many extra data you have to read and from where you have to read. You might read from RAM, you might directly read from the registers, you might read from a peripheral device. That peripheral device is just another term for your input and output devices. Or you might want to write them to your memory or peripheral devices, or you might want to flash them inside your secondary memory. And there comes the secondary memory, and this can be your, let's say, SSD or a drive, for example, and we typically call them as files. So these are the the slowest memory, and this is the faster memory. But like a cache, a register is like more than 1,000 times faster than main memory. So there is a cache that facilitates this process, and ALU and a register, they are like too much faster. Like when you are saying saying that I have like 3.2 gigahertz system. Okay, that means what, that your computer is able to perform these kind of instructions, this kind of instructions, uh, 3.2 billion times per second. Okay, and every performation is called a cycle. Okay, and that and this is given to you by another pulsating system that keeps on and off, on and off, on and off to keep your whole system running, and that we call a clock. So a clock is part of the processor, but we strictly don't consider it as a like part of the processor in general. But that's what basically your processor or your CPU means. Like when programmers talk about CPU, they only consider the processor. Okay. but also like your motherboard, it has the main memory and the secondary memories, and it also has a thing called bus, okay, which are just the circuits that transfer data between main memory and secondary memory and main memory and processor and so on to different pins. Now, if I go even deeper than that, then that will be semiconductors, and we don't want to delve there right now. So that's how your typical program works. Now, we will be looking it at assembly level first to get just an experience to what and your executable file holds. That is the idea we are looking at. So it has a couple of sections. Like first, it has your like where your program starts. Okay, that is your start, and then these there are separate levels. Okay, like you define your start, and like here you say that okay, the first instruction is move, and AX is a register that is inside my CPU, and move the value 5 to AX. Then I'm saying that move the value 10 to the BX register of my chip, and then I'm saying that take the whatever the value is there in the AX register and whatever the value of is there in the BX register, and add them together, and this additions result will be saved to AX register by default, and actually it will come to accumulator, and depending on the like how the system is designed, how the chip is designed, it may directly go to AX register, and also depending on like what this particular action means, like this action in most probably will mean that you'll add those two values and store those values to the first slot that was provided, that is your AX register, and then you take the value from the X register and you store it somewhere different in your in a different register called CX register, and so on. Okay, and this particular section is called your text or code section. Okay, but your like you have some other sections, like this is called your text section of your program. So we call it text segment or something like that. Okay, so it's basically this thing, and your executable actually holds this section, that is most important. Then on top of the text section, it has actually they call it like this section text, and then they have some other sections, like for example you at first you want to declare key whatever you are taking from the whatever values you already want your program to have present or initialized before it starts executing this code, and that is your basically your static section, like static variables, static data or declarations, whatever is there. And I just forgot what the term is, but you can search on the internet. And then it has like your stack and so on, different kinds of other sections defined. But that's what your execution, like your exe file look like if it was if it was not in zeros and one, and like translated into like human readable zero and ones, that is your binary code. But as you can see right here, like it's very difficult to maintain very large amount of instructions in this manner. So what happens is that you have some languages that are directly written on top of this, uh, and they take these kind of direct expressions, like I can say that result is equals to 2 plus 3, for example, and it converts it into something like this, for example. Okay, and then maybe it will store CX into result. Okay, so it will take this, your compiler will take this and put it here. And this is this compiler, the code it takes is written in a little bit high level language, but not high level, we will call it mid level language. And such languages are C, C++, Rust, and so on. So, or even you can think of Java as an example. And then there are high level languages, okay, like for example Python or JavaScript which are typically executed in interpreters. And what interpreters do, interpreters are just programs, and what they do is an interpreter like what an interpreter will do is interpreter is just a program sitting there. In case of compiler, it will output a program. Okay, compiler will output an executable program. And what an interpreter will do, let's say interpreter, is it will take a script. We generally call it script, and then run the script inside itself, and that's it. It might produce some output and so on. Okay, so that's the difference. In case of compilers, you get a program that you can execute. In case of interpreters, they just take a script and run it. They don't give you any executable and such stuffs. Well, there are libraries to like get around it and do stuff like that. But like at the end of the day, that is the thing. And here comes the languages like C and C++, which are very efficient because they are directly translated into something that the machine understands. And because they are translated into something that the machine understands, they are operating system specific. Like for Windows, it will be a different code. For Linux, it will be a different code. For Android, it will be a different code, and so on. But along with that, what compilers give you, the thing called optimization. Okay, the thing called optimization. What optimization does is it eliminates, like, it optimizes your code. That means that you might have some code that is being called again and again and again, but it need not to be called because the outputs are never used at the final stage, so they are just like wasted computation. So it will remove those things. The same way it will do memory optimization. That means that it will try to optimize whatever let's say memory you have. And the same way, uh, like your if your data is being stored at different sections of your RAM, it might take multiple tries for your control unit to get those memories into the registers and so on. So it might arrange your memory in such a way that it will be faster to execute. And the third is the time optimization. Okay, in some cases it will use some instructions that are faster. Let's say I want to perform four additions in example, and my CPU already has four cores. Rather than taking one core and giving one variable at a time and doing one addition at a time, will take four cycles. But let's say I put four values inside the four cores, and then I ask LLU to like simultaneously execute for each core, and each core has its own ALU. Each core has its own register. The cores have some shared registers, and the cache memory is like common between the cores. Okay, and so on. So these are like a very high level things. It will do something like that. For one of such things is called an SIMD. That is single instruction multiple data. You have multiple data on which you want to perform a single instruction. So these kind of things will have happen. And by code, an example is dead code elimination. For example, memory optimization may refer to restructuring the code to use less memory. So these kind of operations, the compiler is smart enough to do for yourself. And for that scenario, in most of the cases, you cannot write faster assembly than a compiler. So the best way to gain performance are lower level, like mid-level languages like C and C++ and Rust and so on. But and that's one reason that and that keeps languages like Python, JavaScript, and these not make doesn't make them that much faster, because in case of interpreter they have to like read that whole script, and then they have all of them, they have some like stacked base machine itself, and that machine runs those instructions one by one. So there is first of all, this step is mostly missing in those kind of environments, the interpreters. Although like most of the interpreters nowadays, like for the critics, I just want to mention this, but this is not what I am trying to say, is that they use something called as JIT. JIT stands for just in time compiler. Okay. So what it does is when a code section of the script is interpreted, and when the interpreted code section is there, it might take that interpreted section and try to produce a efficient binary for the like the interpreter itself, because it contains that stack based execution system at the core of it, and so it might run the code a bit faster, but still it's not an executable that you are producing, so it will not be as fast. That is the first reason why Python, JavaScript, these languages is slow. The second, because this level of optimization that the compiler can do on the entire code can never be done, because the interpreter itself cannot be modified. Okay, but every program, it has its own advantages and disadvantages to take into considerations. So if your interpreter like says that do addition, there is no way to tell your interpreter that whatever you have implemented inside you, produce that. This is the data, just use SIMD. You can't do that. That is one thing. The second thing is that most of these interpreted languages, they are dynamically typed. That means that you don't specify what kind of data you are sending. You don't specify I am sending a number, or I am sending, let's say, text or something like that. So the interpreters, they take your code and they understand that what kind of data you are trying to deal with, and depending on that data, it executes the code. So the benefit that this kind of approach provides is less code, first of all, and also, like, because you are producing some less code, you want to have some trade off in exchange, and that trade off is like you have more high level features. Okay, like which we try to call them abstractions, which means that some of the things are hidden from you. Abstraction means nothing but some of the things are hidden from you, abstracted from you. So you don't have to like care about all those nitpick things to like have everything in your mind to create and program that executes faster. In most of the cases, like doing some research work, like for example, you are trying to make a machine learning model, or you are just trying to show some simple graphics applications, like your most of the applications, websites, so on. It makes sense to use an interpreter, like using a compiler and creating your own program. It's just overkill for that. But let's say you want to create a database system, you want to create a program that will operate your Rocket, or let's say you want to write an operating system. The operating system has to be as fast as possible. So in that cases, you will use a compiler and compile them to binaries. Okay. We can talk about operating systems in a later video. It's not the goal of the thing, but the operating systems are just a kind of way that manages your memory, like a system that manages your memory allocation, deallocation, and it manages how your RAM is behaving, how these particular programs that you are trying to execute are sent to your actual processor, and how to like switch between different programs to do multiple tasks. There are some routines there. They handle those things, and a set of instructions like this are called a routine. Okay, that is also an important term that you should know, that a routine is nothing but I I forgot ROU I think ROUTI routine or something like that. It's a set of instructions. Okay. And this is a micro instruction that is directly understandable by your system, because this micro instruction, your chip, it has control unit which can decipher this micro instruction. Depending on that, it will trigger the buses and it will take the correspondent data to the appropriate registers, and then it will ask the ALU to perform those operations on the appropriate registers. And what programming in languages like C and C++ provide is that, like compiled languages provide, is that uh, you have that fine tune of control. Like I want to only use this memory. I want to optimize this section. I don't want to like go in the general code. The more your program becomes generic, that is an interpreter, it's more generic. And in case of compiler, it's first of all more optimized and more specific. It's specific to the need of your program. Okay, like for a database, you want it to be as fast as possible. For same goes for a noise. And the third thing is that to achieve that, you have to write more code. Okay, this is the downside. Okay, this is